So in the last lecture we discussed few introductory things about thermodynamics that include few terminologies associated with all these things, and we talked about few properties as well. What's the traditional definition of pressure, and then we talked about buoyancy force and some other thing as well, density and specific volume, and we have come up with some ideas about intensive properties and extensive properties. Okay, so I think those ideas are quite clear. Okay, repeat. Can you repeat the question?
The intensive property is independent of mass.
Intensive property is independent of mass. Okay. Then what?
So you said density is an intensive property.
Density is an intensive property. Fine. And this is density per unit volume. Don't forget about the other aspect. It is density per unit volume. Okay. It is mass per unit volume. It is not the mass only. It is mass per unit volume, right? So that's why, because you need to see what is the whole expression, right? So I mean, this is something which should be treated as mass per unit volume, not only the mass. If it is independent of you can say that combined effect or the additive effect of all of the property values at different points in the system, it is something which is, and by the way, it is quite you can say intuitive. I mean, instead of looking at that mathematical expression, just think about something, that if you find out density at this point, density at that point, density at the other point, would you combine all the densities to find out the total density? Not at all. I mean, this is a point value, right? So this is it's a cumulative value for the whole system. So that is quite intuitive. This is mass per unit volume, just to answer your question. It is not only the mass. Okay. Any other thing? But similarly, if you look at okay, I think I have answered it. Any other thing? So let's move on. Look at some other properties as well. This is temperature. By the way, you might have heard about this statement. This is a measure of kinetic energy of molecules in a system. In a chemical species or in any object. Okay, this is a definition. Generally, you think about temperature in this term. Now, there is another thing, that generally we also, if we come to a more simple, you can say simplified definition, this is kind of hotness or coldness of any object. Okay, so now before defining this thing, I think we should look at one more thing. By the way, how do you define temperature? I mean, there should be some starting point, that okay, if you say that these two objects have same temperature, what does that mean? That those two objects have same kind of coldness or same amount of hotness, isn't it? So before going for the definition of temperature, I think we should look at, just to understand what does that describe. We defined this term in the last lecture, thermal equilibrium. Okay, so if you have one object which is, you can say, hotter object, then there is another object which is colder one. So what you can see is, if those objects are coming closer to each other and then you join their surfaces, so something would start flowing from the hotter side to the colder side. Okay, and that something is basically what? Heat, right? And after some time you would see that the volume of this hotter object would start decreasing and the volume of this colder object would start increasing, right, after some time. And this is happening due to some change in property. This is happening due to some change in property. Now after some time you would see that their volumes, or you can say that their hotness or coldness, it becomes qualitatively similar. Qualitatively means if I just touch it, I can say it is hot, it is cold. This is qualitative, right? So after some time you would feel that their hotness or coldness, it becomes quite similar, right? So it means that to describe that kind of behavior, no change in the properties of both these systems, hotness or coldness, and then you say that they are in thermal equilibrium. Why? Because if you join their surfaces, that something which is known as heat, that is not going to flow from one object to the other one anymore. Do you understand that? So this is something which is known as thermal equilibrium, that there is a stage. By the way, equilibrium means it's a kind of balance. I hope you understood what balance means. One upward going forces is being balanced by the downward going forces. Okay, so this is something of balance. So once those two objects have the same kind of hotness or coldness, you say that they are in thermal equilibrium. Why? Because something has been balanced, and what is that something? Temperature, right? Temperature has been balanced. So generally what you see is temperature. If you look at any temperature measuring device, just look at any temperature measuring device, you see a thermometer. It may contain mercury or let's say alcohol, that red thing in that thermometer, or let's say that white thing and silver kind of thing in your thermometer. Or similarly, if you go to some other, let's say more sophisticated temperature measuring devices, just like thermocouple, right, or just like some other temperature sensors which may be installed in a complex electronic circuit. So just consider that those electronic circuits would be measuring temperature based upon the current flowing inside them. And how do you quantify that current? Obviously that current is dependent on the resistance, right? So you see that you always associate temperature with some other property. You associate, in the first case you associated that temperature with, let's say, volume. You have seen that the hotter object would be basically what? A greater volume, and a colder object would be having lesser volume. If some temperature of some body is increasing, its volume should increase, it should expand, the object should expand, right? And if you look at the other side, which is a more sophisticated device, its temperature is associated with what? Resistivity, some other property, right? So this is how you measure temperature. So let me define something about it. I hope you understood this, right? So this is quite clear that you are trying to understand the temperature by what? By measuring some other property, right? And it is something what? Qualitatively it is the sense of hotness or coldness, but to define the temperature, it is very difficult to exactly define the temperature, just like pressure. Obviously, it is a measure of kinetic energy of molecules, but you can't trace all the kinetic energies of all the molecules and then you can average them. You can't do it, right? So what you do is that you associate temperature with some property, and you come up with the conclusion that okay, fine, I am going to measure that temperature with the change in that property. How does it happen, right? So okay, please put that Google map off. Alongside there is first law of thermodynamics, not the first law in that sense. This is the first in the sequence, right? As serial number 1 law of thermodynamics. This is known as 0th law of thermodynamics. It gives you, it describes, by the way, something about the thermal equilibrium. So I have already defined thermal equilibrium, so it is the time to define 0th law of thermodynamics. When two objects are in, this is M, please understood it, this is M, are in thermal equilibrium, with the third object, they are in thermal equilibrium with one another. This is basically statement of 0th law of thermodynamics. Now what does that mean? You have a temperature measuring device just like a thermometer. You put it on one object, it gives you a temperature of, let's say, 100 degrees centigrade, and then you go for another object and the temperature of the other object is also 100 degrees centigrade. Now what does that mean? That third object is the temperature, right? So both of those bodies, they are in what? Thermal equilibrium with the third object. What does that mean then? That those two objects are also in thermal equilibrium with each other. So, and similarly, if they are in thermal equilibrium with each other, what does that mean? They are having the same temperature. Okay. Yes, obviously, that's how you can measure the temperature. No, obviously that would be. By the way, if, for example, if you look at the temperature of this body and let's say that bench, these are two tables. I just put my thermometer over there and see what is its temperature, and then I would go there. Even if I make them, I establish some kind of contact between those two bodies, would the heat start flowing from one object to the other? Not at all, right? So it means that those two objects are also in thermal equilibrium. So that's how basically you define the need for designing temperature measuring devices. I would say this is basically something to design a temperature measuring device, right? And that something is known as thermometer. Okay, that something is known as thermometer, or you can also call other devices as thermocouple. Obviously, it depends. So how do you define it? Okay, any object with at least one measurable property that changes as its temperature changes can be used as a thermometer. You see that basically that domestically used thermometer, very common. If you have some alcohol in that basically tube, a small tube capillary of that thermometer, what you see is when temperature increases, it starts climbing up. What does that mean? Its volume is increasing. So that is the property. Similarly, I told you about something related with the thermocouple. Its resistivity changes, right? So this is how you define it. The particular substance, by the way, such a property which is being used to measure temperature such a property is known as thermometric property, and that particular substance that exhibits the changes in the thermometric property is known as thermometric substance, right? So these are few things which should be introduced at this stage: thermometric property, thermometric substance, what is a thermometer. So obviously please make sure to understand this thing, that sometimes, not sometimes, generally it is very difficult to define temperature straight away. So you have to associate it with some other property, and then you go for temperature measuring devices. Okay? And what is the basic law which is basically providing you the base to, this is the zeros law of thermodynamics. So please go back and read some other stuff related to thermometers, just like thermometers or some other gauges in your book. So what about the units? I told you there are 4 units. What are those 4 units? Okay, first one is Kelvin, then we have centigrade, okay, then we have Fahrenheit, and then we have Rankine. Okay, so I mean, you must have seen their definitions in your elementary physics books. Have you? How do you define Kelvin? Okay, do you know anything about absolute zero? Basically it is equal to what? Minus 273.15 Kelvin. Okay, so I hope you know what are their interconversions. Do you know that? Okay, let me define it. Please no talking. Oh yes, thank you. This is absolute zero, so it would be equal to 0 Kelvin. Thank you so much. Okay. So you can say generally accepted SI unit for temperature is Kelvin, and this is basically the Kelvin scale. Is an absolute thermodynamic temperature scale temperature scale that provides a continuous definition of temperature valid over all ranges. So you can say this is something which is absolute. Absolute means you can't go beyond this. You can't have -1 Kelvin. This is the minimum thing which you can see. And by the way, still it is ideal. Still it is ideal. So this is how it means, valid over all ranges. It means whatever you have physically happening, whatever the phenomena or whatever the system you have, all the temperatures can be defined using this scale. Okay, doesn't matter how cold your object is, it can't go lesser than 0 Kelvin. So by the way, how do you develop it? I think we should. Sorry? No, that's how you calibrate it. That basically boiling point and the freezing point, it is generally related with degree centigrade or degree Fahrenheit. So that Kelvin is something beyond that. Okay. So how people have developed it, I think we should wait for some time, so that I can introduce you guys with something like entropy or second law of thermodynamics, right? So, but just understand that this Kelvin is something which is the absolute scale, Now there is some other definition of Rankine scale. This is how you convert it. .8 into Kelvin. This is how you convert from Kelvin to Rankine. Okay, 1.8. So you can see that absolute 0 in the Rankine scale is equal to absolute 0 in the Kelvin scale, right? Yes. See this thing. This figure is showing you, by the way, is it visible to all? So this figure is showing you few points. Just see that absolute 0 just see for absolute 0 on Kelvin scale it is 0, and then it is calibrated as -273.15 degrees centigrade. On Rankine scale it is also 0. Why? Because it is 1.8 times something. And then on Fahrenheit scale it is -459.67. As you move up, there comes the second most important point, is the icing point, where temperature starts converting from the liquid state to the solid state, right? So this is what is known as icing point. This is 273.15, which is 0 degree, and then 491.67 on Rankine scale, and then 32 degree Fahrenheit on Fahrenheit scale. Then there is one very important point which you should keep in mind. This is the triple point of water. Any definition about it? All the three states are present on this scale. Yes. So let me define this triple point. The triple point of a substance, so it's a Wikipedia kind of definition, just to make you understand what that is. The triple point of a substance is the temperature and pressure at which the three phases ice, steam and water coexist. Yes. Yeah, generally we define those temperature scales with respect to water. Why? Because you have to come up to a conclusion that okay, fine, this is something which is the standard thing. This is something which is available to everyone. Okay, so you can't define those temperature scales based upon something very rarely found out. Okay, so this water is used for defining all these things. Then there is a steam point, and by the way, this triple point is almost equal to 0.01 degree centigrade, right? And then steam point, which is 373.15, and you can see that this range is divided into 100 points. From icing to steam, you generally divide it into 100 points, and that's how it means, that's how you calibrate it. For example, I would say that if mercury it expands itself to this length, just consider that it is 1 degree centigrade change. Then if it becomes double, if its length goes to a double point, you can say that it is 2 degrees centigrade. So this is something which is known as calibration. Okay, you would see those things in your course on instrumentation. Sorry? This is the triple point of water. No, it's a point, 0.01 degree centigrade. It's a point. Okay, it is not a range, by the way. It is not a range. These, I think you are confused by these two lines. No. This is something which is showing you icing point exactly at 0 degree centigrade, and this is something which is giving you triple point of water. Right? Oh, I don't think I would be able to answer it. I don't think I have something about this question in my mind now. I can see and let you know if I find some answer. Okay. Okay. Any other point? No point? Okay. Topic. The second topic is based upon energy and the first law of thermodynamics. Okay, so before going to define energy, I think we should look at few other aspects. Like for example, we should understand what is work, we should understand what is kinetic energy, we should understand what is potential energy, we should look at, you can say, their interconversion, right? We should look at some other definitions related to equilibrium. How do we define it? And specifically, we should be able to understand how we can measure work or energy in thermodynamic systems. Okay. So obviously your previous knowledge would help you in grabbing those concepts, but let me start from defining work and kinetic energy. Okay, fine. Just look at this object, this figure, the right hand side figure, this one. So just look at this body. it is basically following a certain path, and once you try to define any property, you have to define first what is your reference frame. Right? So you have to define what is your reference frame, and to define your reference frame, so for reference frame you define reference directions, and then after defining those reference directions, you do what? You define some 0 point, some origin. Okay, so after defining that origin, let's say I assume that this is the origin point. Obviously, conventionally, it should have been the intersection of both of these 2 points, but this is something which is my starting point. I say that if this is the object is at this point, it has 0 displacement, right? So you can say that it is following a certain path. It is following a certain path, and then if it is moving, it should be moving under the action of some force. Okay, under the action of some force. That force may be this thing, F. Now that force can be decomposed into 2 components: along the path and normal to the path. Right? If this is the curved direction, this is a curvature, so you would see that this tangent to this curve would be direction along the path, and then this is something which is the normal direction, which is being represented as Fn. You would see those kind of decomposition in your dynamics course, inshallah. So this force component would change the magnitude of velocity. This force component would change the direction of the velocity. Remember that. Okay. I'm not talking about that thing. Just think that it is moving in a plane. I'm looking at it from the top. So the distance which is being covered by this object is S. Just to make it a general thing, I would say that it is S. So my point is, how would you define change in velocity? My point is, how would you define change in velocity? Just think of that Newton's second law of motion and tell me, how would you define it? mdv by dt, what should it be equal to? Fs. It should be equal to Fs, right? So the second thing is, this Fs, it is a function of S. Do you understand that? As body moves in this path, along this path, its force would change. And by the way, you can represent that force as what? As a function of S. It means at this point, this body would have this force. At the other point, the body would have some other force, and then so on. S is kind of the displacement, not the distance. Displacement. So what you can see is, keep this thing into your mind, and I would say that if Fs is equal to mdv by dt, I can say that this becomes equal to mdv by ds, ds by dt, and then I would write it as if this is Fs ds equals m v dv. Why? Because this thing would become velocity. Okay, so if you know that this Fs is what? It's a function of S. It would change the direction. That's what I told you at the very early stage. How does it define it? I won't go into that detail because that's a topic in dynamics. I just need to use this concept to define work. Okay. So otherwise, just understand that normal component is there to define to change the direction, right? And by the way, how does that? How does it do it? Okay, just to answer your question, you know that it is R, and R is being defined by some magnitude and some unit vector, if you take its derivative, v is what? dr by dt. So these are two terms. So one derivative would be the magnitude of r by dt, and then this would be straight away multiplied by that term, and then you would take its derivative, and then this would be coming straight away with as a multiplicative factor. So that second factor would be defining the change in direction. So that's how they are related to each other. But I won't go beyond that. So fs ds equals mv dv. You know that this fs is a function of what? S. Okay, fine. Then I would say, if you integrate it, if you want to find out the total force, so what would you do? Total force, or you can say whatever the total phenomena was. So what you would do? You would integrate it from S1 to S2, and obviously at S1 you have velocity V1, at S2 you have velocity V2, and this is equal to this thing. Okay, function means, fine, just look at this object. At point S1 it would have some force, at point F2 it would S2 it would have some other force, S3 it would have some other force, and let's say if you plot that force, it may be a straight line, it may be a curvature, it may be a parabola, but somehow or the other you know that this F is depending on S. So in technical terms, in mathematical terms, if it depends on S, I would say that it is a function of S. You understand it? That force is not constant, obviously. Yes. It is the second law of motion there. This is subscript S. Can't you see it? This is subscript.
Even S is defined as the distance between origin or the body as it changes. Or
Yes, you can say that.
For example,
It depends. I mean, this is a very general plot, but if you want to keep all the things very synchronized, you can have this origin at this S equals 0 position. But this is a matter of your understanding. I mean, this is what my S is 0, right? So otherwise you can always keep it on origin, no problem at all.
No, but sir, as the body changes position, will be marked as points as S1, S2, or will it just mean the total distance?
No. It would be like S1, S2, S3, S4. Yes, it would be. By the way, this is a very tricky concept when you come to the definition of work. So let me define it first. And so you can say that this Fs ds from S1 to S2, it is equal to m integral from V1 to V2 V dv. Then how you can define this integral? I hope you understand this integral. It's very common kind of thing. So this is m, which is a constant. Then you can say this is half v square from v1 to v2, and then you can say m by 2 v2 square minus v1 square. So this is what? Because it is related to velocity, it is related to motion, so you would say that it is change in kinetic energy. By the way, kinetic energy is represented as, let's say what? Half mv square. Okay, and then you can see that this change in kinetic energy, is equal to what? Some product of force and displacement. That change in energy is equal to what? Some product of force and displacement. So it means change in kinetic energy occurs due to some work done by force Fs on the body as it moves from S1 to S2. Do you understand that? Now, a very important thing, I would just give you a clue at this point and I would answer this thing later. Just see, for example, if your body is at S1 and it has gone to a point which is S2, what would you say about work? That work is something which is associated with a point. If the body is, let's say, S2, at S2, would you say that the work on this S2 point is this much? Would you say that? Or let's say work of this point is this one? Would you say that? Not at all. But you would say that if the body moves from S1 to S2, the work done is this much, right? So, I mean, this is a very important concept, that you can't define work as a property. Remember that. You can't define work as a property. I mean, you can't say that work at this point was measured to be this one. Not at all. So if you can't define that work as at some point, it means it is not a property of the system. But energy is a property of the system. Remember that. Okay. So I would reiterate this thing and explain this concept later once I come to more about work. So I hope you understand what is kinetic energy. I mean, whatever the work is being done on the system by the force Fs, that is being stored in the system as it is changing its kinetic energy. So let's come to the second point, the second type of energy, which is potential energy. Work is what? You can say that. Yes, obviously that's what it is done with the change in energy, any kind of energy. Okay. So there is another point. Just look at this figure. You can see an object. There is some force acting on this body in the upward direction. This is R. Then there is some force acting on the body in the downward direction due to the field. This is mg. And by the way, to make it very general, I would say that it is field force. Instead of calling it a weight, I would say it is field force. Okay. Sorry? Why? Because that force is being experienced by the body because of what? It is present in the gravitational field. If you bring that body outside that gravitational field, if you put that body inside, let's say, a strong electromagnetic field, you would see that there is some force from that electromagnetic force as well. So that is why it is known as field force generally. By the way, you should be able to get yourself familiar with those terminologies. What is field force? I mean, these are very generic terms, so more appropriate to think in these terms. So anyways, that object has been taken from this point to that point. So you would see at this point its velocity is, let's say, v1, at this point its velocity is v2, and the position is z1 and the position is z2. Now if I ask you the net force, just remember this figure. If I ask you, tell me what is this change in kinetic energy equal to? It should have been equal to what? Force, that R force multiplied by dz, and dz is what? It has gone from z1 to z2, isn't it? And then there is another force which is acting in the downward direction, so it was what? Mg, and it is also applied for a distance from z1 to z2. Okay, so you can say that this z1 z2 r dz would be equal to half mv2 square minus mv1 square plus mg z2 minus z1. You haven't taken R square? Okay. So this is something which is known as change in kinetic energy, and this is something which is associated as change in potential energy. Okay, change in potential energy. So I mean, you should understand that potential energy depends on the position of the object in the field. Remember that potential energy depends on the position of the object in the field. If you are in the gravitational field, it depends on the elevation, right? So as you move up, your potential energy increases. As you go down, your potential energy decreases. If you, let's say, if you throw somebody and it is having a free fall from some height, it is going down, so its what? Its potential energy would be decreasing. And where is that potential energy going? As an increase in the kinetic energy. Okay, remember that. So you can say that energy is of the system is conserved but it can change its form from potential to kinetic, kinetic to potential. That's how you do this thing. Okay, so overall this is the thing, and it is due to the work done by some force R. That change happens due to what? By some force R. Okay, any question about this thing? Yes. Can you understand this term? I think you should. This integral? Okay, you are talking about this thing? Okay, I mean, if I just write, for example, if I just write, can you understand this thing? Let's talk about their units. What are the units for energy or kilojoules? Okay, then you have Newton meter. By the way, this is how you define joules, right? Newton meter. So some of the interconversions are given in your book. You can see that how you jump from one unit system to the other one. Obviously this is force, so it may be pound force, and then it may be in inches or feet. So you should understand that this is what energy units are in British engineering systems. Then there is something related to BTU, right? So please go back and check how they are interconvertible, those energy those unit systems. So anything related to it? Any question? Very elementary stuff. Yes or no? Okay, let's talk about then something little complex. More appropriately, I would define work. You know, force is a vector, and same is the displacement. So that product may be a dot product. That product may be must be a dot product. I mean, why must be a dot product? Because this is what? scalar quantity, right? So let me define work in a more technical term, and then we would move on. Now this is the definition of work. I mean, in every system you won't be putting some kind of force on a system, on some object, and then you would try to lift it. You won't be doing it any time. Now for example, if I ask you, you heat something and that gas starts expanding, how would you define that force on the gas? You won't be able to define the force, and literally a force. You won't be saying that this heating phenomena is applying this much of force on the gas. You won't be seeing it. Okay, so on in case of mechanical objects, you can literally see how much force is being applied on some object, how much displacement it is having. But in thermodynamic systems, if you try to heat something, I repeat my point, you won't be able to quantify that force. Although you can see how much, let's say how much that you can say the top of that gas, that top cover of that gas is going up, is elevated. So that is quantifiable, but you cannot quantify the force. So you have to do something about defining work, right? So we need to define work in a more general sense. I would write down the definition and then I would explain it. So let's talk about thermodynamic definition. This is thermodynamic definition. Okay. Work is done on a system, okay, or by a system on its surroundings if the sole effect on everything external to the system could have been the raising of a weight. The most important thing in this definition is the last line. Could have been the raising of a weight. Could have been. It is not actually. Like if you are drawing a current from a battery, you won't say that work is not done by the battery on the system, isn't it? But still, if you integrate that battery with some kind of motor, that work done by this battery on the system can be what? Used to raise a weight. So it could have been. I mean, this is a philosophical kind of definition, but you need to understand that all the time, specifically for thermodynamics, especially for thermodynamic systems, you won't be looking at work done as if you are lifting a weight. All the time you won't be looking at that lifting of a weight. But you should understand that this work is done by the system on the surrounding if the result of that something is what? Lifting of a weight. Could have been the lifting of the weight. Could have been. It might be the case, right? It is not always the case. Sorry? No, could have been. I mean, if you go sideways, I mean, still. Now, why are you using the word lifting? I mean, against the gravity, against the field, right? So similarly, if you do it in this direction, so obviously you are applying force. So you are moving it in the field. So in both cases, you are doing what? Changing the position of the weight. Okay, just see this thing. A very interesting example. Look at this assembly. This is a container with a gas inside that. This blade is being driven by that motor. and then this is the battery. Now this dashed line is representing what? Control surface, which is giving you a boundary for this system. So this gas is a system. Similarly, this battery is a system. So this is system A and this is system B. Now just see that once you drive this blade, it would move. Obviously it would try to move the gas molecules around it, right? It would try to stir the gas, and if it is trying to stir the gas, it means it is doing some kind of work on the gas. So some kind of work is being done on the system. But I mean, would you be able to find out the forces applied by the blades on the gas molecules? No, sir. You won't be able to do it. But somehow or the other, you know it, that you could have lifted some weight by the rotation of this blade. You understand that? So this is a philosophical kind of definition. I mean, this is not a mechanical kind of definition. This is thermodynamic kind of definition for work. Similarly, go back and see this battery. The current is drawn from this battery due to some kind of voltage difference, right? And if you look at this voltage difference, can you define work based upon this voltage difference and the current flow? For mechanical engineers, it is very tough, right? So, but still you understand that if you somehow or the other, you associate some motor with it, this voltage, this driven, you can say driving of the current due to that voltage difference could have been converted into something that could be used for lifting a weight. Could have been used. I mean, so it means from the thermodynamic principle, because it is could have been used. So you can say that work is being done by system B on surroundings. This is something which is work done by surrounding on the system. So I mean, these are two different things. One thing is you have work done by the system on the surrounding, and then you have work done by the surroundings on the system. So how do we define it? So let's talk about the sign convention about work. Work would be positive if it is done by the system on the surrounding. Okay. Similarly, this would be negative if it is done on the system by the surroundings. Right? Now, okay, there is one reading assignment for you guys. There are some situations in the mechanical systems, I mean, you are trying to lift some object, literally lift some object. You would see that work is done on the system by the surrounding, but you would take it as if it is positive. Right? So please go back and see what is that situation and why do you see it? Why do you see that work is positive even if it does not follow the upper definition? Okay, somehow or the other it is related with energy interaction. So please go back and see why do we do it. By the way, it is an important thing, again a philosophical difference. So I have also defined work is not a property. Work is not a property. It means I won't be saying that within this reference frame the body at S1 would have work at W1. I won't be saying it. But how would it be described? That if the body would go from S1 to S2, the work done would be equal to W. I mean, this is delta W. Although it is delta W, obviously you would say that it is what? Fs2 minus Fs1 kind of thing. That's what you would describe it, right? But somehow or the other you can't define as if it is W2 and it is W1. You can't say it, isn't it? So please try to understand this thing, that work is not a property. You can't define work at a single point. You can't define it as if it is a property, and it won't be an element of state. I hope you understand what that state is. State is what? A subset, a set of properties. So how people define it? I mean, if the body has gone from this point to this point, this is S1, this is S2, and we would say this is W, but to define it, generally you would say this thing, delta W, right? Delta W. So this delta W is, although it is not a property, although it looks like non-physical thing, but to define it mathematically, we call this thing W as if it is delta W, not from W1 to W2, I would say this is from point 1 to point 2, and this is known as inexact integral. Okay, once again, just be very careful. I would explain it once more. If the body is going from point 1 to point 2, some work would be done on it. Would you say that this is W1 and this is W2? You won't be saying it. What would you say? That the work is being done to bring this body from point 1 to point 2. But mathematically, you do that with all the other properties. I mean, how did you define this work? You define this work as if it is going from S1 to S2. Now this is what? You can define force on state 1. You can define force on state 2. Physically you can define it. So this is known as an exact integral. But if I just try to interpret this in terms of integration, just try to integrate. I would not use the word d, I would say this is delta and this is from 1 to 2. And this is W. You know that this thing is physically not possible. You can't define it as if it is a property. So there is some kind of, you can say, what should I use the word? Some kind of contradiction between mathematics and physics. Some kind of contradiction. So that is why I would say this is an don't get confused. We would use these expressions in the upcoming discussion. Right now I am just defining few things, just trying to give you their conceptual basics. Okay, so this, whenever you see this delta kind of thing, W, this is what? Inexact. Inexact means that this integral is not related with some property. You can't define it on some state. They are always defined when you have taken the body from one point to the other. You can't define it. But if you see some other integral, just like this one, something like this, D symbol, it means you are talking about exact integral, and this property could have been defined on 1 and 2, all the states. This property could have been defined like this, but otherwise this delta thing won't be defined on one point and the other point. Okay, so this is something very important to understand. Then let me define last point for today's lecture. This is power. Okay, so power is what? Time rate of change of what? How much work has been done in a certain amount of time, right? How much work has been done on a certain amount of time. So if you see that, I would describe it as if it is W dot, which is being represented as P. I won't use the word P because it is also used for pressure. So let's not use this symbol. Instead, we would use this W dot. So in engineering, you would, if you put that dot onto some symbol, it means you are taking its time rate. And if you see this dash sign, it means you are taking its derivative with respect to some spatial variable. Spatial variable, it means this derivative could have been dV by dx, right? But if it is V dot, what does that mean? So this is a generally accepted convention in engineering books, in engineering literature, that this dash belongs to this spatial derivative. Spatial, I mean this one, SPATIAL, derivative with respect to some spatial variable, space variable. And this dot is giving you what? Time rate of change. So this W dot is time rate of doing work, and that would be equal to F dot V. Right? So these are two vectors. Similarly, if I define W from this power definition, I would say that it is F dot V vectors dt, and differentiation would be, integration would be from T1 to T2. Sorry? So this is about the inexact integral. Once you open it, you would, this is what? This is an exact integral. You can find the force, you can find the velocity at point 1 and point 2. But here you can't do it. So instead of writing it as this one, I would use this thing. And if once it go on the other side, it can become D. Okay. So just remember the things between delta and small d. So that's all from my side for today's lecture. In the next lecture, inshallah, we would go on to some other things, thermodynamic work, right? And that would be related to PV diagrams, and then some other energy points we would also look at. Thank you.